Welcome to all in the lecture series of functional analysis. Now in this lecture we see about the linear functional, bounded linear functional. So firstly we see the definition of the linear functional. A linear functional is a linear operator with the domain in a vector space and range in the scalar field k of x. And therefore we write down f be the linear functional which is from script d of f to k, where k equals to r, that means the scalar field is r if x is real, and k equals to c, that means complex if capital X is complex. Here from the definition we see that the linear functional is a linear operator, that means every linear functional is a linear operator with the additional condition is that for the linear operator we have the condition that if t is a linear operator, then we write down script d of t from t with the mapping which is from script d of t to y. Here we consider dt, that is a subset of x, and here x and y both are the vector spaces. X and y both are the vector spaces. T with the mapping which is from script d of t to y, and for the linear operator it is a linear operator. T is a linear operator, that means whose domain lies in a vector space and range it is in a vector space. That means here this domain is actually a vector space, and next we prove in the theorem that the range, that is the script r of t which is a subset of y, it is also a vector space. This is about the linear operator. That means t is a linear operator. It means that domain is a vector space and range, that means script r of t, lies in a vector space. This is the condition for the linear operator. Now here in the definition of the linear functional, here we have to given that the linear functional is a linear operator. That means f is a linear operator with the condition that domain it is in a vector space and the range, that is k, and the range lies in the scalar field k of x. That means the script r of f, it is a subset of k, and this k it is nothing but the scalar field of x, because x is a vector space, therefore x has a scalar field and that scalar field is k, and as f is a linear functional, that means its range lies in a scalar field of x. That is the condition for the linear functional. And therefore here when we say that x is a real vector space, that means its scalar field is real, and then in this case k equals to r, and then f is the mapping from script d of f to r. But when x is a complex vector space, that means its scalar field is complex, and then in this case here we get k equals to c. This is about the linear functional. Now after defining the linear functional, we define the bounded linear functional. Now the definition of bounded linear functional. A bounded linear functional is a bounded linear operator with the range in the scalar field of the norm space capital X in which the domain script d of f lies, and thus there exists a real number c such that for all x belongs to script df, mod of f of x, that is less than or equals to c into norm of x. Here in this definition we observe that as we say that a linear functional is a linear operator, in the same way here bounded linear functional is a bounded linear operator with the same condition that with the range in the scalar field of the norm space x in which the domain script d of f lies. That means here the mapping f which is from script d of f to k, it is a linear functional. It is a linear functional whose domain, that means script d of f, lies in a vector space capital X, and as capital X is a vector space whose scalar field is k. And therefore one more condition for this linear functional is that this f is a bounded. That means f is a bounded linear functional if and only if f is a linear functional with the condition that there exists real number c such that for every x belongs to script d of f, mod of f of x that is less than or equals to c into norm of x. Now here in the for the bounded linear operator, if t which is the mapping from script d of t to y, we say that it is a bounded linear operator. For the bounded linear operator, the condition for boundedness is that norm of tx that is less than or equals to c into norm of x. This is the condition for the bounded linear operator. But for the bounded linear functional, this condition becomes mod of f of x, it is less than or equals to c into norm of x. Now here our condition that is mod of f of x, and here we have the condition that is for the norm of tx, because this is a operator. This is an operator, and therefore here we are writing norm of tx, and this is the norm of tx. Here this is the norm on capital Y, and here Y is a norm space. But for the bounded linear functional, which is from script d of f to k, here we know that for the bounded linear functional, the codomain is k, and k is a scalar field. As it is a scalar field of x, therefore it may be real or it may be complex. If x is real, then k is real. If x is complex, then it is complex. And therefore in both the cases, the norm on k, it is nothing but the mod. The norm on k, it is nothing but the mod, and therefore here the condition that is norm of f of x, it becomes mod of f of x. And therefore instead of writing norm of f of x, we are writing mod of f of x is less than or equals to c into norm of x. This is the definition of the bounded linear operator. Now after defining the bounded linear, this is the definition of bounded linear functional. Now after the definition of the bounded linear functional, we see the value of c for the bounded linear operator is that norm of tx, it is less than or equals to norm of t into norm of x. We see it for the bounded linear operator. In the same way, here this equation becomes mod of f of x, it is less than or equals to norm of f into norm of x, where this norm of f is like this. As here we have the norm of t, this is defined like this, it is equals to the supremum over x belongs to dt norm of tx divided by norm of x. In this way we define the norm of t. In the same way here norm of f, it is equals to supremum over x belongs to script d of f. The one more condition is that x must be not equals to 0. Here also we have the condition x must be not equals to 0. Now instead of norm of tx, here we have mod of f of x divided by norm of x. This is the condition for norm of f. Now after this, in the same way for the norm of t, another formula is that norm of t that is equals to the supremum over x belongs to dt norm of x equals to 1 of norm of tx. That is the another formula for norm of t. In the same way here, the formula for norm of f becomes norm of f that is equals to the supremum over x belongs to script d of f norm of x equals to 1 mod of f of x. This is the formula for norm of f, and hence with the help of these two formula we can write down mod of f of x, it is less than or equals to norm of f into norm of x. This is about the bounded linear functional. As we define the linear functionals on a vector space capital X, now we consider the set of all linear functionals defined on a vector space capital X. That means here we consider the set of all f such that f is a linear functional defined on a vector space capital X. We collect all the linear functional which are defined on a vector space capital X and we give it the name that is X star. Then this space, it is called as a algebraic dual space. This space, which is the collection of all the linear functionals defined on a vector space X. This space, it is called as a algebraic dual space and it is denoted by X star. Its algebraic operations of vector space are defined like this. If f1 and f2, these are the any two elements of X star, then we define the sum, that is f1 plus f2. It is defined equals to f1 plus f2 of X and it is equals to f1 of X plus f2 of X, where small x be any element of capital X. This is the sum defined on X star. In the same way, if alpha be any scalar, then we defined alpha f of X, that is the scalar multiplication with respect to f. Alpha f of X, it is equals to alpha f of X for all x belongs to capital X. In this way, we define the addition and scalar multiplication on the space X star. And with this addition and scalar multiplication, X star again become a vector space. That means X star be the set of all linear functional on a vector space X. On this X star, that is the algebraic dual space X star, on this algebraic dual space X star, we define the addition and scalar multiplication. With these two operations, X star again become a vector space. As it is a vector space, then we again consider the set of all G such that G is a linear functional defined on a vector space X star. That is, this is nothing but the collection of all the linear functional defined on a vector space X star. Then we call it as a second algebraic dual space and it is denoted by star of X star because it is the dual space of X star. That is, therefore it is called as a algebraic dual space. That is the second algebraic dual space of capital X. Again here X star of X star, that is equals to X double star. It is equals to X double star. X double star with the set of all the linear functional defined on a vector space X star. Now we define the relation like this. Space, general element, and value at a point. Value at a point. Now we consider the space. Here we consider the space X. In this vector space X, the general element is small x. Okay, it does not have any value. Now we have the X star, that is the set of all linear functional defined on a vector space X. In X star, the general element is f and the value at a point of f, it is f of X. This is the value at a point. Now as we show that x star, it is again a vector space. Therefore, on this x star we define a linear functional, and the set of all the linear functional, it is denoted by x double star. That is the second algebraic dual space of x. In this second algebraic dual space, the general element is G, and value at a point, it is the G of f, because this G, it is applying on x star, and therefore it gives the value G of f. In this way we have the space x, x star and x double star. We see the general element of these three spaces. Also we see the value at the point. Here we observe that if small x is the element of the vector space x, on this vector space we define a linear functional f. Therefore f is applying on each element of this vector space, and therefore we are getting the value, that is f of x. In the same way, x star, it is also a vector space. On this vector space we define a linear functional g, and therefore G is applying on x star. That means G is applying on each element of x star, and therefore here the value at a point is becomes G of f. Now here we can obtain G belongs to x double star, which is a linear functional defined on x star, by choosing a fixed small x belongs to capital X and setting like this. That means here we have G, which is the mapping defined on x star. G is a linear functional defined on x star, and therefore here we have the value G of f. But f is a linear functional which is applying on x. Therefore here we are getting the value gx of f, and that is equals to f of x, where small x belongs to capital X, it is fixed, and f belongs to x star, that is variable. That means we can obtain G belongs to x double star, which is a linear functional on x star, by choosing a fix. Here we fix small x belongs to capital X, by choosing small x belongs to capital X, and then the variable is f belongs to x star. F is the element of x star. That means for any f belongs to x star, we are calculating the value f of x. Here if we have f1, f2, f3, these are all the elements of x star. Then for this fixed small x belongs to capital X, we are getting the element f of x. Another is f1 of x, f2 of x, f3 of x, and so on. And then here we get the linear functional, that is G belongs to x double star like this. G of f, that is equals to gx of f, that is equals to f of x. In this way we obtain the element G belongs to x double star. Here we start with the element small x belongs to capital X, and we fix this element. Let small x belongs to capital X be fixed. Then corresponding to this element, as here x star be the set of all the functional f, such that f is a linear functional. F is a linear functional on x. X star be the space contains all the linear functional on x. That means here if f belongs to x star implies that f is the mapping from x to k, where k is nothing but the scalar field of a vector space x. Now f is applying on capital X, it means that f is applying on each element of capital X, and here small x is the element of capital X, and therefore here f is applying on this x, and we are getting the element f of x. Now f of x is the element of capital K, that is f of x is a scalar. Now after that, if we consider another element, another vector of this x star, that is f1. f1 be the any element of x star, that means another element of x star. Then again we get that here again we get f1 is a linear functional on x, that means f1 it is again a mapping from x to k. Again f1 it is applying on capital X, therefore it is applying on small x, because small x is any be the element of capital X, and therefore here we are getting the image f1 of x. Now this f1 of x it is again a scalar. After that we are taking another element f2, which is also the element of x star. Then again we get that this f2 it is the mapping from x to k. Again here f2 is applying on this x, and we are getting the image that is f2 of x, it is again a scalar. Continuing in this way for each element of x स्टारच्या प्रत्येक एलिमेंटवर प्रत्येक एलिमेंट हा ह्या पॉइंट स्मॉल एक्स वर अप्लाय होईल, आणि त्याच्यावर अप्लाय झाल्यानंतर आपल्याला मिळणारे स्केलर्स कोणते राहतील, एफ ऑफ एक्स, f1 of x, f2 of x and so on. This is continue for all the elements of x star. x star मध्ये जितके लिनियर फंक्शनल्स असतील त्या सर्व लिनियर फंक्शनल x वर अप्लाय होऊन मिळणारा स्केलर कोणता राहणार, f of x, f1 of x, f2 of x and so on. Now corresponding all these images, corresponding all these scalars, now we define a function g. We define a function g like this. G of f it is equals to f of x. We define g of f1 that is equals to f1 of x. G of f2 that is equals to f2 of x and so on. Now here in this define, here we observe that the point x is common to all these, and therefore here corresponding to this x we write down this x is here in the subscript of g, because here in all these point x is fixed, variable is f, f1, f2 and so on, where each f is nothing but the element of x star, and therefore here we are writing gx of f that is equals to f of x. Here we are writing gx of f1 that is equals to f1 of x, gx of f2 that is equals to f2 of x and so on. Now here we observe that we start with the fixed element small x, which is the element of capital X. Now corresponding to this element, here we are taking the images f of x, f1 of x, f2 of x and so on, where each fi is the element of x star. And then using these images we define the function. We define the function like this: gx of f is equals to f of x, gx of f1 is equals to f1 of x and so on. Here we observe that this gx it is applying on f, f is the element of x star, gx is applying on f1, f1 is the element of x star, gx is applying on f2, it is the element of x star and so on. That means the function gx is applying on each element of x star, and therefore we are writing gx is a mapping from x star to. Now gx of f is equals to f of x. f of x is the element of k. gx of f1 that is equals to f1 of x. f1 of x is the element of k. In the same way, gx of f2 it is equals to f2 of x. It is the element of k and so on. That means all these images are the scalars, and therefore here we say that gx is the mapping from x star to k. x star to k. And therefore here we are getting corresponding to the element small x belongs to capital X, we are getting a function gx which is from x star to k. Defined like this: gx of f is equals to f of x. That means for gx applying on f, and here we are getting the value f of x. f of x it is nothing but your gx of f. This is the mapping Gx, which is from x star to k. As Gx is the mapping from x star to k, we are getting the mapping Gx, which is from x star to k. Now, this mapping is a linear functional, because here if we take f1 and f2 be any two element of x star, and we are taking any two scalar alpha and beta, and then Gx of alpha f1 plus beta f2. This is equals to, by using this definition, here the definition of Gx is like this. Gx of f, it is equals to f of x, where f be any element of x star. Here the small x is fixed, variable is f. Therefore Gx of alpha f1 plus beta f2. By using this definition, it is equals to alpha f1 plus beta f2 of x. Now we know that f1 and f2 are linear, and therefore it is equals to alpha f1 of x plus beta f2 of x, and that is equals to alpha in bracket f1 of x plus beta in bracket f2 of x. But f1 of x, it is nothing but Gx of f1 plus beta into Gx of f2. That means here Gx of alpha f1 plus Gx of alpha f1 plus beta f2, it is equals to alpha Gx of f1 plus beta Gx of f2. From this, here we get that Gx is a linear. Gx is linear. After that, here Gx is a function which is applying on a vector space, because x star is a vector space whose scalar field is k. That means it is a functional, and it satisfies the condition of linearity, and therefore here we say that Gx is a linear functional on x star. That is, Gx is a linear functional on x star, and as Gx is a linear functional on x star, it implies that Gx is the element of x double star, because x double star is a space containing all the linear functionals on x star. And therefore in this way we start with any element small x belongs to capital X, and corresponding to this element we are getting the element of x double star. By using this, here we get the mapping. We get the mapping C, which is from x to x double star. That is the algebraic dual space. Second algebraic dual space of x. Defining like this, we start with the element small x. Now with the help of this element, we are getting the images f of x, f1 of x, and so on. For all fi's belongs to x star. Collecting all these images, we define the mapping Gx of f, that is equals to f of x. Gx of f1, that is equals to f1 of x, and so on. And in this way we get the mapping Gx. We show that this mapping Gx is a linear functional on x star, and therefore Gx is the element of x star. That means corresponding to the element of capital X, we are getting the element Gx, which is the element of x star. That means here x to Gx. In this way we get the mapping C, which is from x to x double star. By using that, x goes to Gx. This mapping C is called as the canonical mapping. C is called the canonical mapping. The canonical mapping of x into x star. Sorry, not x star, x double star. C is called as a canonical mapping of x into x star. Now here we prove that this canonical mapping is linear. Canonical mapping C, which is from x to x double star is linear. This mapping is defined like this: C of x, because small x is the element of capital X and x here goes to gx. That means C of x, it is equals to C of x, it is equals to cx of f, and it is equals to f of x, that is nothing but gx of f. In this way we define the canonical mapping Cx. Now here we have to show that this canonical mapping is linear, and therefore we start with any two element of capital X. We take let x comma y belongs to capital X be any two arbitrary element of the vector space capital X, and alpha comma beta be any two scalar. Then C of alpha x plus beta y. Now it is applying on f of f. It is equals to, by using this definition, it is equals to gx of, not gx, here g of alpha x plus beta y of f. Now gx of f, it is equals to f of x, and therefore it is equals to f of alpha x plus beta y. Now f is linear because f is the element of x star. X star be the vector space of all linear functional on x. Therefore f is a linear, and therefore here we get that it is equals to alpha f of x plus beta f of y, and it is equals to alpha into f of x means gx of f. Therefore it is equals to gx of f plus beta into gy of f, but it is nothing but alpha into cx of f plus beta into cy of f. In this way we show that the mapping C, that is the canonical mapping, is linear. This implies that canonical mapping C, which is from x to x double star, it is linear.